Well, a very good afternoon to all of you, also to the audience. Welcome. Hereby I open officially this academic ceremony in which Ms. Mudita Vats will defend her academic thesis entitled From Farm to Table, Mass Spectrometry Imaging in Traditional and Innovative Foods. May I invite you to present a summary of your study and the conclusions of your thesis in your next 15 minutes, and I give you the word.
Thank you. Dear Pro-Rector, dear members of committee, dear supervisors, colleagues, family, and friends. I'm going to give an overview of my last 3 years of PhD entitled From Farm to Table, Mass Spectrometry Imaging in Traditional and Innovative Foods. Food comes from different sources, which can be plant-based, animal-based, or processed. We eat food to derive nutrition and enjoy flavor, which comes from the molecules. And these molecules are influenced by agriculture practices, animal husbandry practices, and processing parameters in industry. So it is important to look at the molecules that are in our food. For performing molecular analysis, one of the techniques called liquid chromatography mass spectrometry, or LCMS, can analyze flavor compounds, phytochemicals, nutrients, and contaminants. However, we need to make a smoothie of our sample before we introduce it into the mass spectrometer. Now, in the smoothie, we know what is there, but we don't know where it was localized on the original sample. Now, if I make a pizza out of my vegetables, I know where each of these vegetables are localized. That is what we do with MSI, or mass spectrometry imaging. Suppose there's a slice of carrot, and there are different anatomical structures in it. MSI can reveal what are the different molecules distributed in these different anatomical structures. It adds a complementary feature to the existing mass spectrometry. So let's go into one of the techniques that I've used in my thesis, matrix-assisted laser desorption ionization, or MALDI-MSI. Here we take a sample, make thin slices of micron-meter ranges, and lay it on top of a glass slide. The sample is sprayed with matrix, and the matrix-coated slide goes into the mass spectrometer, where a laser shoots on the sample. And what matrix does is it helps the molecules in our sample to release from there and ionize. The laser moves pixel by pixel, generating a photograph, just like we make with our phones. And we obtain a mass spectrum of mass to charge versus intensity. In this mass spectrum, green, red, and blue correspond to 3 different compounds in 3 different regions of the sample. Here we make, from molecular information, we make an image. another technique called desorption electrospray ionization, or DESI. As the name suggests, we don't use matrix, and a charged stream of solvent is employed on top of the sample, and the ions are propelled into the mass spectrometer, giving us the spatial distribution of compounds. And now that we have a basic knowledge of mass spectrometry, let's go into the contents of my thesis. It has a review chapter, spatial distribution of taste compounds, spatial ingredient classification of burger, temporal dynamics of viticulture, and I'm going to cover chapter 3 to 5 in this presentation. Starting with the localization of flavor compounds in mushroom, the taste profile of mushroom has bitter, umami, sweet, sour, and salty compounds, which are contributed by different molecules. And these molecules are they can be present in different anatomical structures, or maybe they're all over the mushroom. So to understand that, we took a fresh frozen mushroom, just like how it is in the natural state, and then we mimicked the cooking conditions by heat treatment. And then amino acids are a huge part of taste profile, but the ionization efficiency is low. So to enhance the ionization, we chose an on-tissue derivatization approach. I was able to look at the distribution of taste compounds in different regions. For example, here, the glutamine, which is umami flavor, was more intense in the gills, highlighted by white or yellow according to the intensity scale. So white or yellow is higher intensity, and going towards blue or purple is lower. And then bitter tasting, sour tasting, sweet tasting. Now you will notice that upon heat treatment, there is a reduction in the intensity or migration of compounds. Might be because when we were heating the mushrooms, not only the water, but some of the compounds were also migrating through it. Another observation was lipids. Lipids are carriers of flavors, and they are odor-active compounds, so it was nice to see their distribution. One of the interesting observation of TC36-4 in the end was more intense upon heat treatment. Maybe this is why we enjoy baked or cooked mushrooms. So in conclusion, the information we got with MSI can help in the extraction of flavor from different parts of the mushroom or other food products. And if you want to tweak flavors or other molecules, we can change processing parameters and give consumers what they demand. Moving on to my next chapter, temporal dynamics and organic viticulture. Grapevines often suffer from downy mildew, which looks like oily spots on the surface of leaves. And as the disease progresses, you will see that the berry withers and turns dark in color, and it affects the organoleptic quality of wine. So the farmers often apply herbicides and pesticides to get rid of it. However, due to environmental and health concerns, a farmer here in Limburg region makes use of essential oil, and he rubs essential oil on the surface of leaves. Essential oil can trigger plant immunity and provide protection against the disease. So we were curious to see if the essential oil is applied on top of the leaf. Does it affect the bacteria growing on the surface of the leaves? The bacteria, of course, are also composed of molecules. So we wanted to see some changes in their molecular composition. So we performed bacterial identification and mass spectrometry imaging of 3 specific bacteria in the presence of essential oil. So to see if the bacteria growing close to the essential oil and far from the essential oil have any molecular changes. And then we were interested in looking at the surface of the leaf discs, and we cut out the leaf disc and performed mass spectrometry imaging of it. However, the leaf surface has cuticle. It's a waxy layer, which is a barrier for us. We can't see what's inside. So we made cross sections and performed MSI to look into metabolites and lipids of the cross sections. So to do this, the samples were collected from May until August at 7 different time points. However, considering that the grapevines are natural ecosystems, so they have their plant development and other environmental factors, so essential oil is not the only thing that we can see if something is happening because of the essential oil. It can happen due to different things. So we went to a greenhouse and collected samples of control, treated, infected, and a plant that was first treated and then infected. So we got a great overview of the bacterial identification. There were different bacteria at different time points. Some of the bacteria were also common in a lot of time points, and such overviews can help in having a reference of monitoring plants' health. And then going into the mass spectrometry imaging, there were 3 bacteria, Lactobacillus, Pantoia agglomerations, and Pseudomonas. I picked these 3 because they were one of the biocontrol agents. And upon essential oil treatment, the organic acids and some other compounds in the bacteria change. So one of the examples is aspartic acid that was more intense in Lactobacillus close to the inhibition zone or essential oil, and the rest 2 were more intense far from it. So the effect of essential oil was species specific. And then looking at the metabolites or lipids. So diacylglycerol is one of those lipids that participate in the structural composition of the membrane. So we noticed that there is a change in intensity after time point 2. So there's a treatment and then slightly higher intensity. And then there's second treatment after 5th time point, and again there is slight change in the, actually a good change in the intensity. But due to other factors, I cannot pinpoint that this change is only due to the essential oil. It can be due to other reasons. And then in the greenhouse, we saw an accumulation of acylceramide on the infection spot. Might be that the defense mechanism of plant involves accumulation of certain compounds on the infection site. Then in the cross-section, there's no surprise that healthy samples have a higher intensity of SQDG, which is also a diacylglycerol present in thylakoids. And the infected ones have a lower intensity as we lose the photosynthetic area upon infection. So the study on grapevine gives us a great overview, adds a lot of knowledge in the existing studies, but due to a lot of factors, not just essential oil, it is difficult to pinpoint, but it is interesting to know. So the bacteria and metabolites kept fluctuating, and we have an overview study. Now you are going from farm to table. So here there's a meat burger. Of course, it is derived from meat. And meat has specific structures and spatial arrangement. For example, muscle fibers and adipose tissues. Now, a lot of people want to move from meat-based to plant-based diets due to environmental and health reasons. And plant-based derivatives give a different spatial arrangement of, for example, adipose tissue. So it is important to understand these spatial distributions in order to mimic the products as close as to the meat-based products, and also to find, for example, food fraud if there's an additional component inside your food that is not mentioned on the packaging label. And what goes behind these arrangements are the molecules. So what we did is we performed some mass spectrometry imaging and used that information in machine learning models to answer 3 questions. One of which was adding a piece of meat intentionally into a vegetable burger to see if the machine learning model can segment that piece of meat. Then we looked into different vegetables to classify, so we classified the different vegetables in the vegetable burger. And lastly, we wanted to see if this model can distinguish between 3 different burgers. So the usual workflow, we took the vegetables and burgers from supermarket, made cross-sections, and performed Marley and Desi MSI. And then the data was imported into the machine learning models. So we were very happy to see that the segmentation was successful, and we saw a piece of meat in red and the rest of the vegetables as well getting segmented. Then with Desi MSI data, one thing is that the models are versatile and work for both Marley and Desi. And here we were able to see a separated corn and carrot. So here you see with the yellow. And then finally, the 3 different burgers had 3 unique compounds. So each of the burger had a unique compound that was only present in that burger and not in the other 2 burgers. So with this spatial information, we can add such MSI-based machine learning models into the processing pipeline to give quality products and improve consumer experience. This thesis showed how mass spectrometry imaging can unveil molecular complexities of food from farm to table. Thank you. Now I give the word back to the prorector.
Thank you very much, Ms. Candidate, for your clear presentation. And I compliment you with nice illustrations. And I would say it is a tasty experience which we're going to discuss now. But before we start, I'm going to introduce your team, which has brought you in 3 years and 1 month to this afternoon here. And in front of me, and I would like to mention this to the audience, we have the members of your promotion team. And I would like to mention here from my list, in the middle sitting here, Associate Professor Silero Pastor. She is Associate Professor in Spatial Omics for Neuroregenerative Medicine. And also sitting beside to her is Dr. Kuipers. She is Associate Professor in Mass Spectrometry Imaging in Perioperative Diagnostics. And then finally, the first promoter is Professor Heren. He's Professor in Molecular Imaging, all at our university. And for the audience, we have 6 members in the Corona, 5 are here present in the aula, and 1 member will be online and will be on the screen later. Saying this, we're going to start swiftly and exactly on time. And I'm going to start with Professor Jonkers. Professor Jonkers was also the chair of your assessment committee, and she is professor in intestinal health, and I'd like to give her the first opportunity to discuss with you.
Thank you very much. Dear candidate, I really would like to congratulate you and your supervisory team with this very interesting thesis. It's really a new angle which you addressed, a lot of appreciation for that. 3 of the 4 chapters have been published, so that's very nice, and it includes a very nice detailed review, and that was very interesting for me because I learned a lot from that because I'm not an expert in mass spectrometry, so that's very valuable. And I also want to see how I can use these data and learn from that from my own perspectives. So I would like to discuss with you chapter 3 in a little bit more detail, and you indicated that you focus on traditional and innovative foods. I guess the mushrooms might be part of the traditional one, or maybe they become innovative. We will see later after the discussion section. And you focused with MSI to look for the flavor distribution in edible mushrooms. And maybe a very general, simple question to start off. Why did you choose to study those mushrooms?
Highly esteemed opponent, thank you for your question. The honest story is that a company was very much interested in looking at some compounds in the mushroom. And to start with, I just went to a supermarket to buy white edible mushrooms. And mushrooms not only are good for flavor, but also the nutritional profile is great. My personal interest was to move into the nutrition after flavor. But yeah, with the time constraints, it is only the flavor that you can see in the thesis.
Yeah, okay, so it is a bit of coincidence, but also I hear that the flavor, that is an interesting topic for you. Nice to hear that. So I would like to go with you to page 80, where you have figure 3.5, where you looked to the different metabolites in the fresh, frozen and the heat-treated samples. And you already mentioned the umami flavor, which is quite specific for mushrooms. And there you see, for example, this nice distribution in the fresh frozen mushrooms, but also in the heat-treated mushrooms. For example, the glutamine and the glutamic acid, you also showed it nicely on the screen, which really increased then in the heat-treated mushrooms. You mentioned this to be transfer of compounds, maybe, but I really see a substantial increase of the concentration. So how do you explain this high concentration in the heat-treated?
I'm sorry if I said increase in the presentation out of nervousness. Actually, it was a decrease in the intensity upon heat treatment.
It was a decrease in intensity?
Yes.
Okay, so it was, okay, that I misinterpreted myself. So there was a decrease upon
Yes.
heating,
Yes.
because it was then not the purple blue color I had to look at, but the lighter color.
Lighter color are higher intensity. Sorry.
That explains a lot. Thank you very much for clarifying that. So you really saw a decrease with the heat treatment in the oven.
Yes.
And I think we eat a lot of mushrooms, a lot of people.
Yes.
Mostly we bake them or we cook them, and especially the cooking. Would you have expect to find a different profile then compared to your oven-baked mushrooms? Less of a decrease or?
So I chose oven because one of the things that sometimes happen is if we cook in a pan, sometimes the mushrooms start sticking, and if we are using oil, then that is also changing the molecular profile of the mushroom. I have not tried. Some people in other research groups, they take frozen mushroom and that they heat with on the pan. But they're not doing imaging, they're doing the smoothie technique. So I have to try to be sure.
But given the water content, maybe would it matter, for example? Because if you do them in an oven, they shrink to some extent. If you cook them, then it might impact. Do you expect that it could impact the metabolite that you see them?
Yes, they shrink in the oven. I use 140 degrees Celsius, and I also see some water drops coming out and slight shrinkage on the size. And yes, the intensity of metabolites decrease because the water that is getting released is also taking some of the metabolites with it, I suspect.
Yeah, so it's really interesting to look further into that.
Yes.
And then maybe one of your parents, so that they can also do a little bit of work, would like to read out the title of your thesis.
Okay. From farm to table, mass spectrometry origin in traditional and innovative foods.
So we're not discussing the traditional or innovative, but from farm to table. I was really caught by that. I think that's really very interesting. Because if I look, for example, to this metabolite profile and, for example, the food industry, how could they use your data to improve their products? What do you think? What would be your thoughts about that?
So one of the things is that a lot of flavor compounds or the flavorants that we get in the industrial products, they are chemical based and not natural, and from mushrooms we can have natural and what we call as clean label taste compounds, and they can be extracted from specific structures. For example, it is only in the gills of the mushroom or on the stipe. Then why to do a bulk processing of the entire mushroom? Just take one piece of it. Another thing is that if you know that when the mushrooms are growing, so at each stage, when the mushrooms are small, then they're bigger, and then they're ready for harvesting, there are changes in these mushrooms or other, even in plants, with the growth. There are changes in the compounds. And those compounds, we might be enjoying them as taste, but must be for other processes in the plants. So now if we harvest the mushrooms at different times, it has also been shown in literature that there are differences in the taste profiles. So we can tell the industry that harvesting at certain times can give what consumers demand or what they want. Mm-hmm. Another thing is tweaking processing parameters. Maybe so mushrooms are sold as fresh, pickled, freeze-dried, and in different forms. So, what are the processing parameters for heating or pressure that we use? They can tweak that to give the desired product.
Okay, then I don't have.
No, I'm sorry.
Then I'll happy to discuss further with you to see how we can collaborate in the future on this topic at a later time point. Thank you very much for your.
Thank you.
I apologize. I have to be a little bit strict. We have 5 more members.
Yeah,
okay.
you're correct.
So the opposition will be continued by Professor Vriesen. He was also a member of your assessment committee, and he's professor in plant functional genomics, and I assume from our campus in Venlo. And by that, I would like to thank you that he came all the way from Venlo to Maastricht. Thank you.
Thank you very much for the introduction. You assumed right, but I came from Utrecht this morning, actually. But dear candidate, I liked reading your thesis very much. It's completely different. It's not my expertise. There's such a technology, the MSI. So my expertise is much more in plant genetics, in the genes, but these genes make the components that you measure. So there is a quite clear link. I also have one question that's related with application. And maybe one of your paranymphs can read out loud proposition number 3.
Localizing the taste compounds aids in developing tailored mushroom flavour profiles.
So remember the tailored profiles a bit. And then on page 85, you also say, the knowledge gained about the special distribution of taste compounds will help the food industry to modify the flavor profile to improve the experience of consumer mushrooms. But who is the consumer, and how do you know what he likes or she?
Highly esteemed opponent, thank you for your question. Yes, I think it's kind of a continuation from what Professor Jonkers was talking about. Who are the consumers? I mean, I have not personally talked to the consumers. One of my colleagues in the consortium is talking to the consumers, and she has published how people are liking mushrooms and other alternatives. But what I can provide is different localization of different compounds in different regions of mushrooms, and not just flavor, but also, which is not a part of my thesis, I could also see vitamin D derivatives. And I think I have to try with an industry to have a tailored profile and then a tasting panel.
Thank you. Yes, it was just, I know it's a very difficult question. I mean, I'm from the seed business where we always were talking about traits of crops, but the point is who likes what, and that is different per region and so on. So it's very difficult to talk about the consumer. And
yes.
Maybe we can go to another topic. On page 125, you mention in the present study the distribution of gibberellic acid and abscisic acid, and then between brackets, tentatively identified with isotope simulation, was visualized in all leaf discs. Mm-hmm. What is this isotope simulation?
So if you enter the mass, for example, of abscisic acid, and you know the isotope pattern of a compound, and if in your data you see that exact isotope pattern, then you can confirm that this is, for example, abscisic acid. These compounds, such as phytochemicals or hormones, are so low abundant, especially for MSI, that we see smaller intensity of those compounds. So I was not able to identify them with fragmentation because it is so low abundant that fragmentation doesn't give you any information. So I performed isotope simulation for confirming.
So is it possible, do I understand that it is not possible with this technology to identify endogenous plant hormones?
It is possible, but it is challenging. So some of the endogenous compounds you can see by derivatization approaches. So we spray or coat our sample with a certain compound, and then like a matrix, and then that adds a mass to the compound. For example, TAHS was adding 177, and then we can see that in our spectrum. So there are certain endogenous compounds in literature that they've published with MSI. However, it's challenging, and when you have a targeted compound that, oh, I want to see this hormone, and then we can look at the structure, and then which derivatization agent can work on it to give us the spatial distribution of that. But because I was doing untargeted, so I cannot bias by only using a derivatization or an approach that will give me one compound, but maybe not others.
Okay, so yeah, I can go more to this, but maybe later, because I think it's very interesting. It would be an added value if it would be possible, especially maybe at cellular level. But I have another question, and that's more a question. Yeah, that's really a question. So I have a project that's about finding plant varieties with optimized flavonoid composition. Actually, flavonoids have health effects, and we want to have as many as possible. So this is a project where we want to analyze many varieties, but we do it with HPLC. Mm-hmm. Now I have the feeling that we are doing it a little bit in old-fashioned way. Is that so?
I will not call it old-fashioned or call it or downgrade it, because for certain questions we need HPLC separation. You will not see the spatial distribution of compounds, and if you really want to have it in a specific structure, but with HPLC you will know what is there, and then maybe we can complement both. But yeah, definitely it will be interesting to discuss that project with doing the MSI. Sorry, did I answer your question, or I got excited with the project?
Yes, so what I saw in your thesis is that you measured two flavonoids, quercetin, conjugated form of quercetin, yes, and another flavonoid. So what was that other flavonoid? Or
SQDG, are you looking for?
No, it was really called another flavonoid.
Ah, yes. So 469.12, again, the abundance was low. And if I try to match it with a database, when I enter this mass in a database, the database shows that the class of compound is flavonoid. But if I go to a specific flavonoid, then the mass error was more than what I can be confident about. That if the mass error is lower than 3, then I know it is this compound, but it was more. So it falls in the category of flavonoid, but I cannot pinpoint which flavonoids. So that's why.
Okay, thank you very much.
Thank you.
Thank you very much. Then the opposition will be continued by Professor Honing. He was also a member of your assessment committee, and he is professor in systems imaging at our university and the Institute M4I. Give you the word.
Thank you, Mr. Prorector. Dear candidate, a lot of congratulations in pushing analytical chemistry and especially mass spectrometry imaging in food science. And also congratulate the supervisory team. And I use the word analytical chemistry because analytical chemistry is also about definitions. And I see sometimes a little bit fluffy type of terms you use. For example, you have a sentence saying molecules within plants interact in different ways. And then I read the sentence again and I ask myself, yeah, what are you wanting to say? You are not specific enough. And you speak about agro-food systems, and that does not tell me anything, so it's very broad. Now, I would like to ask one of your paranymph to read proposition number 7.
Long-term investigations on the effects of repeated essential oil applications are required to understand the temporal dynamics of organic viticulture.
So again, long-term investigation. So what is long-term?
Highly esteemed opponent, thank you for your kind words and question.
Is that 1 week? Is that 2 weeks? Is that a millisecond?
So I don't know the duration because we don't.
But you wrote it down. You don't know the duration.
Yes. So the effect of we don't know how long the essential oil effect lasts, and what we see is due to the effect of essential oil, or is the effect of essential oil gone, and what we are seeing is something else.
Yeah, but now you're speaking about the effect of the oil. I'm just asking you about what do you mean with long-term investigation, And then you use also temporal dynamics. So
I would say multiple years of...
Years?
Yes, to be sure.
And temporary dynamics, what does that mean? Because dynamics are per definition time dependent. So why temporary dynamics? Do they change in time?
It's temporal. Yeah, so what I observed was that the microbes and metabolites and other compounds were changing
that's
the
dynamics.
whole time. Yes.
Yeah, that's sufficient dynamics.
Yes.
Okay. So we are agreeing that in terms of understanding the dynamics of molecules in biological systems can be at different time scales. That's more specific then.
Sorry, could you repeat?
So the investigation of molecular processes in food, for example in leaves or whatever, microbiome, is time dependent, the dynamics. And you can investigate that at different time scales.
Yes.
That's more precise.
Yes.
Do you agree?
Yes.
Yeah, then we agree. That is also... Because I have another question on definition, because you speak about complex polydispersity, but polydispersity is complex. So why do you use complex polydispersity? In your text, I have that page somewhere. Page number 43, you use the word complex polydispersity. And I use polydispersity in polymer chemistry and...
Sorry, can you, page number 43?
43, just the 6th sentence below pesticides and heavy metals. You just want to say the dispersity of all the types of molecules in your biological system. And I agree then, but hopefully you agree that complex polydispersity is a little bit complex to understand.
Yeah, that's true.
Okay, let's go to science, because you have also some tables which intrigue me, and I would like to discuss that with you, and especially on, let me see, page 45, and that's of course not your data, but
yes.
I start to be very intrigued. When I look to this mass spectra, I see a lot of adducts of two molecules with sodium, potassium, and protonated, and the ratio between these ions changes upon the area. And when I look to this picture, it looks like the abundance is dependent on the area, but I don't understand that, because it should be dependent on the ionization. So what's happening here? Do you see figure 2.7 on page 45?
Yes.
So there's a lot of mass spectra,
yes.
and in area 2.2 there is nothing. We suspect that, but especially when you look to the ratio of the different adducts, they changed a lot in time or in an area. Is there an explanation for that? It's not your data, so I don't push you too much.
Yes, at this point I am not sure about what was more in the paper. I was mainly focusing on the distribution of, for example, pesticides with imaging techniques.
Yeah.
And
no, but let's leave it like that. But then, for me, this was an intro to a very important, very interesting table. That's your data. That's on page 77. It's on the identification of the lipids, and especially here also, I see some PCs which have a sodium adduct, sol, or only the sodium, and the other one, the potassium. And and in the case of PC 36.4, I see both, but in PE 36.4, I only see the potassium. So what's behind that? Why is this happening? And can you use that to identify your molecules?
You're saying that with PC 36.4 there is sodium and potassium, and with PE 36.4 there was just potassium.
Yeah, or for example, PC 38.2, I see only the potassium. And it intrigues me always why in some cases you see a sodium and potassium, and sometimes only a potassium, or sometimes even only a protonated molecule. And that in itself can tell you something about structures, of course.
I am not sure about the reason behind not finding sodium adduct in these two
It's difficult
that-
because in Maldi it's difficult to
Yes.
understand why things happen. And maybe, that's enough, Prorector? Yeah, okay, so thank you very much for your good explanation.
I'm sorry. We have to proceed. So we proceed with Professor Ognier. She's professor in environmental sciences in the Josef Stefan Institute in Ljubljana, Slovenia, and I'd like to thank her that she joins us today, and I'd like to give you the word.
Thank you very much for this nice introduction. So, dear candidate, I think that this is a nice piece of work in food science, and I think it will make a big impact in the future. But I have some questions. Specifically, I would like to learn why did you select so different topics, because they are completely different. What are the challenges? What inspired you to do this?
Highly esteemed opponent, thank you for your question. My enthusiasm was mass spectrometry imaging, and I was ready to do any project that involves mass spectrometry imaging and can teach me more and more about it. This thesis is an overview of different types of food and plant-based samples. So we have sown the seeds that
from farm to fork, I would say. Yeah.
For future researchers, and shown different examples within MSI.
And what challenges did you face with the preparation, with the analysis? Completely different, probably. Huh?
Yes, the sample preparation was the most difficult part, especially in my first year, and now I enjoy that the most. First of all, the cross-sectioning. As MSI is more popular in biomedical tissues, and the content of water is less in biomedical tissues, so it is easier than, not always, but as compared to plant-based or mushroom, which has a lot of water. So in the beginning, I was not getting an intact section from the cap of the mushroom till the stipe. Heat treatment helped in getting better sections. As you can see, the thickness of heat-treated and fresh frozen is different. And then with the leaves don't stay flat and attached on the slide. So they lift in the vacuum. So for that, we used freeze drying. So they are very flat and have lost the water as much as possible. And then we fix it with tape. Again, with cross sections, there are a lot of plants that we can section at 5 micron meter thickness, but this was not going below 16 micron meter. And after trying all of these difficult samples, the burger seemed easy with practice. But if there are some chunks of veggies, then they fall out from it.
Okay, but speaking about burgers, so another question tackling this. But do you think that this is important, the location of some compounds in burgers, or for my opinion, as a consumer, not really, but maybe for other things?
You will notice that when you bring a burger from, for example, supermarket, it is not cooked. And then when you cook, if there are different compositions, a meat-based, a plant-based, or something else, the cooking properties on the surface and on the inside, the crunchiness and the mouthfeel is different. So we can, with MSI, we can mimic it. So the cooking properties of a meat-based burger is similar to the plant-based burgers, and that will affect your
So become
experience.
also the culinarically a little bit educated. Okay, and the last question is, we are using the traditional methods, for food fraud. How do you see this mass spectrometry imaging to be in the future a part of the food fraud, actually? And what are the advantages of this mass spectrometry, or availability, for example?
Thank you. That's a very interesting question. Just like we added a piece of meat in the burger, one example is that if there is an unlabeled piece of food inside your burger or any other food, then there are a few researches that are popping up these days in food fraud and authenticity. For example, some preservatives are added. Okay. And sometimes there's a spatial localization of those preservatives in the structure of like bread, and we can find out a spoilage in the food and where it is localized in the beginning of it, and then maybe if a food product allows us to cut and leave that part and maybe use the other part, that will be also helpful.
What about organic production? Does this also have some potential?
You mean
organically produced wine or conventionally?
Yes, of course. Like we can compare the organic with the one used with pesticides, and see if sometimes some endogenous compounds might hinder with the pesticides, or the pesticide absorbs certain compounds sometimes. So, yeah, the comparison with of both.
Okay.
Thank you.
Okay. Thank you very much, and good luck with your future research.
Thank you very much. Then we will continue now online, and I would like to mention Dr. Schumann. He is from the Department of Barilla Advanced Laboratory Research in Barilla in Italy, and I'd like to thank him that he joins now online, and I'd like to give him the word.
Thank you. Dr. Ms. Candidate, I'm very, very, let's say, pleased to have this interaction with you, because I really appreciated the thesis, and especially from my experience from the food, both academic and industry, I really find a lot of engaging for the future in terms of potentialities of the application. You opened the interesting door. And I'm curious to ask you something concerning, in this case, the very first part of your thesis. I really refer, for instance, to what you reported in page 12, when you are talking about contaminants, whether from environmental sources or, let's say, from other sources from, let's say, the field to the food. So I'm curious to ask you your opinion about the potentiality of the techniques you have explored in order to, let's say, localize different categories of contaminants together, let's say, from the spatial point of view in a raw material or in a finished product. Interestingly, also you reported similar consideration in page 21 in the introduction, where you were talking in general about different categories from pesticides to alkaloids, etc. So I'm curious to ask you where you can see synergies between environment research and food research through these kind of technologies.
And for sorry, am I audible?
Yeah, I can hear you.
Yes.
Yeah.
The research on contaminants, I can give you different examples how MSI can play a role there. For example, on pesticides and heavy metals that we can localize with different mass spec imaging technologies such as SIMS. Bringing the environmental and food together, I think it's also going on with the current researchers that are looking into the contaminants. And in my thesis, also I can expand the plant-based, the grapevines to look into different contaminants, not maybe in the organic farming, but the vineyards that are using pesticides. And then, sorry, you had another question?
Yes, we can also move to other questions and consider the fact that, for instance, in the future, also the new dose about microplastics as carriers of pesticides, etc., could be something, for instance, to be explored, but it's just to add something in the discussion. And if we want, we can move to another question. I would like to ask you to focus more on the chapter 4 now, which is the one you were describing, the description of your work about the meat and the burger study. And I want to ask you something about what's reported in page 92, when you were talking about data from DAISY and MALDI that were not combined together. So curious to know if you have had an experience of tentative data fusion coming from collecting data from the different imaging techniques, or if there are some specific reasons for which it's better to keep models separated and extrapolate information in a separate way from the two.
Thank you for your question. Yes, in this chapter, we have not fused any data. The MALDI data was analyzed separately with the machine learning models, and the DESI was analyzed separately. It is interesting to think about if we can fuse the data together. I'm not sure before I try. It will be interesting to try. One thing is that both the modalities give, there are advantages in both the techniques. For example, some of the compounds in MALDI get suppressed with the matrix, which in DESI we can detect them. And MALDI gives you different matrices, so you can go with wide range of compounds. I'm not sure if fusing them will have a beneficial effect or will be difficult for handling the data.
Okay, thank you. And staying on this chapter, if possible, I would like to ask you something about what you reported in page 98, where you were describing the aspect of the several kind of compounds you can isolate in the different ingredients. And obviously, within the ingredients, we have carrots, but we have also the meat, for instance. So you were reporting possible future adulteration detection in page 98 and 99. Can we imagine also to go, for instance, into the meat speciation frauds cases? And can you comment on that?
Repeat the last for the meat?
Yeah. Yes. I mean, can we imagine not only to localize different ingredients in the burger or different kind of, let's say, alternative protein, etc. So following your technique, could you comment about the potentiality for meat speciation? So to look for frauds in species of meat with this kind of approach?
That also, when the meat has this marbling effect on the surface, and that also describes the quality of meat. And yes, we can do mass spectrometry imaging on that. Also, some of the studies perform origin of the meat and distinguishing between, for example, horse meat and beef. So yes, that is possible. There are certain molecular markers, we can say, for different types of meat.
Okay. Do you have any idea of a specific category of molecular marker useful for that? In terms of
no,
categories?
At this point, I don't have a marker on the top of my head.
Okay, maybe peptides, for instance, but yeah.
Some lipids are specific.
Okay.
Yes.
Yes, also lipid profile, I agree with you.
Yes.
Yeah.
Yes.
Yeah. And very final question. Sorry, there is a sort of echo I can hear, but I hope you can hear me.
The localization of certain compounds in different meat is different with the connective tissues or other tissues. So that is also a sign of which meat it is. Yes, that's it.
Yeah, I agree. Mm-hmm. And finally, about the chapter 6, you were talking about outlook, and in particular in the final paragraph 6.3 in the outlook. You talk about future of imaging in agrofood science, promising and multifaceted. So I'm curious to ask you, what can you suggest if you think for the future to make more routinary these kind of approaches from the industrial point of view? Do you have any comments, any suggestion after your 3 years experience to imagine a future for having this kind of analytical approaches more routine, let's say, for the industry.
Yes. One of the options for routine analysis can be a mobile mass spectrometer that you can take with you in the fields and also in different processing steps. The other can be like in this thesis we have shown with the burgers, such models can be a part of processing to detect food fraud or adulteration very rapidly. But I also want to add that sometimes due to the economic reasons, it is not employed as you need expensive tools and an engineer or specialist for it. So yes, there are certain things that we have to consider to make it successful for industry. Yeah.
Yeah, so you suggest that this could be, let's say, a kind of return when you research for developing a new product or something like that, that has a sense, even if not so much economic, let's say.
Yeah, sometimes it can be not so economic. I would urge my instrumentation colleagues to make cheaper mass spectrometers.
Well, thank you for your answer.
Okay.
And I think we have to proceed to the final opponent, which will be Professor Penders. He is professor in metagenomic epidemiology and intestinal microbiology, and I'd like to also give him the opportunity to discuss with you.
Thank you. Dear candidates, I also would like to congratulate you with the wide range of topics related to mass spectrometry imaging applications that you covered. And I would also like to extend my congratulations to your supervision team. And I can also say, because we learned to know you during your time at our department, that I've learned to know you as one of the most enthusiastic and curious PhD students that I've ever met. So congratulations for that. But of course, I also would like to ask some questions, and I would like to move to chapter 5, which contains two of my favorite things, microbes and wine. But the wine we will leave for later, I think. So let's focus on the microbes, because I'm not a plant microbiologist, but we focus mainly on humans. And what we know there is that the variability in the microbiome between individuals is extremely large. So we have a lot of variation between individuals. So I was wondering, how is that with plants? Do they all have the same microbes? How is it with different leaves from the same plant? And related to that is what you did in your studies, taking 3 leaves per time point. Is that sufficient to cover that variability?
Highly esteemed opponent, thank you for your compliments and question. Yes, that's true. The variability is there. In the beginning, for a test, I tested more than 3, and there was not much variability on the surface of the leaves. But yeah, the vineyard is huge, and I have not covered the entire vineyard. So I have to try to look into the variability of the plants that I have not chosen for this study. But for the plants that I chose, the triplicates look like they're enough, and there was not much variability in those triplicates.
Okay. So when then, because you did both culturing as well as sequencing, and if I compare the data, and you probably also did, I don't see a lot of overlap. So why is that? Do you have an explanation for that?
Yes, I had a difficult time in finding overlaps, and I was zooming into the corona pie charts and found a very small percentage of some bacillus species being common. And also Pantoia agglomerans, I think I found in the sequencing as well. Sequencing is much better in terms of also having non-cultivable bacteria. So I suspect that those were more in numbers, and while with culturing and using biotyper, I was only able to see the cultivable bacteria.
So I think that's indeed one of the reasons potentially. If I then look at the bacteria that you cultured, and like I said, I'm not a plant microbiologist, so I had to look some of them up. But what I found out is that many of these bacteria actually produce antimicrobials or even phytohormones, or even can stimulate the immune system of plants, and are actually already being used commercially as biopesticides. Yes. So, and then you see that this essential oil also inhibits some of these beneficial microbes. Yes. Is this essential oil a good thing or is it a bad thing? What do you think?
True, and the real story is that the farmer was using some bacteria to spray on the leaves before he started doing the essential oil experiment. And yes, the bacteria itself were releasing antimicrobial compounds, as you said. And I personally think if it was my vineyards, I would have just sprayed those bacteria instead of essential oil. There was one paper I found which said essential oil has a beneficial effect on the growth of bacteria. So I don't know if it's really bad, because there are more researches that says it has antimicrobial effect against both the beneficial and harmful bacteria. But it's very complex research, and the sample that we have in vineyards to say that, you know, I can't make a statement, but I kind of feel that essential oil is not helping that much.
Okay, but there's definitely more room for additional research, yes, on the maybe probiotics for plants, so, yes, to say. Yes. Okay, thank you. Then maybe a more general question about the application of MSI, because you already said that you want to study everything that has an MSI topic. So maybe also something completely new. You study the microbiome, and you mainly study the spatial chemical distribution. Is there already a place to study the composition of microbial communities? Can you profile the spatial distribution of different microbes in, for instance, biopsy samples? Is that already possible, or are there still some hurdles to take?
So some people are already doing it, but yes, there are hurdles, because if there is an infection that is visible, and for example with a staining technique, and then we do MSI and we can overlay and say that, okay, this region is where the microbial infection is. But in some cases there is infection or presence of microbes, and they're releasing certain compounds. And the researchers working on this are not sure if it is really the compound coming from the microbe or from the body. So the challenge lies there, and also with databases, especially with Biotyper. It's growing, but it's not everything.
Okay, so what do you think is needed to be done then to come to that?
Dear Ms. Candidate, you are allowed to answer the question, but you also can finish. The choice is completely yours.
What more needs to be done is making more databases. For MSI in. I think trying more and more samples and making a list of different researchers to be able to compare the new researches to that. Yeah.
I think we leave it by that. Thank you very much.
Thank you.
So, Ms. Candidate, Ms. Vats, the time appointed for defending your thesis has now officially passed. The degree committee will now withdraw to discuss not so much the quality of your thesis that has been approved already, but the way you have defended your thesis this afternoon. I request that you and your company await the results of our deliberation and our return to the aula. Thank you very much.
Thank you.
The PhD defense has now ended. The degree committee will debate the candidate's performance behind closed doors. This process usually takes about 10 minutes.
Southside, 7 miles in my rearview mirror. I know what it felt like. My goals only getting clearer. East side to the west side. No place like home. If it's questions that you've got, go the extra mile and die. On the line, I know you know that I can't read your mind. Years can't fly by now, don't waste all your time. Cause I'll go the extra mile. Long road to the south side, 10 miles in my rearview mirror. I know what it felt like. My goal's only getting clearer. East side to the west side, no place like home. If it's questions that you've got, go the extra mile and die.
On the dash, got my laces tied. Long road, I don't waste no time. Break rules because fate decides. With the team and we chase the light. I make a move, fall down, shake it off. I hate to lose, bad branch, break it off. No room for negativity, praise and love. Prepare for deep part cause we're taking off.
Take the mileage, traveling so far from home. Gathering knowledge, other connections. I put the time in to get everything I ever hoped for. It's a challenge and we all in. It's a better future that we go for. And even though these nights seem long, I know that I am never on my own. Know you won the battle once you've grown. Outside, 10 miles in my rearview mirror. I know what it felt like. My goal's only getting clearer. East side to the west side, no place like home. If it's questions that you've got, go the extra mile and die. Long road to the south side, 10 miles in my rearview mirror. I know what it felt like. My goal's only getting clearer. East side to the west side, no place like home. If it's questions that you've got, go the extra mile and die. Years can't fly by now, don't waste all your time. Cause I'll go the extra mile.
Dear Ms. Vats, the degree committee here present has assessed the quality of your thesis, your presentation, but also the way you have defended your thesis. In view of its positive verdict and taking into account your previous qualifications, the degree committee has decided to grant you officially the degree of doctor. Professor Heren is authorized to confer upon you this academic distinction in accordance with Dutch university customs, and therefore I invite your supervisor now to take the floor. Thank you.
Please, all rise.
Do you promise to work in accordance with the principles of scientific integrity at all times, to be careful and honest, transparent, independent, and responsible?
Yes, I promise.
Then, by the authority vested in us by law and in conformity with the decision of the committee here present, I hereby confer upon you, Mudita Vats, the degree of doctor and grant you all rights attached by custom and law. As evidence of this, I now present you with the degree certificate signed by the rector, the secretary, and the other members of the committee, and affixed with the official seal of the university. Esteemed Dr. Vats, dear Mudita, congratulations, you've done it, and what a whirlwind ride it was. Today you've completed your PhD in a record time, 3 years and 1 month from the start of your joint journey in October 2021 to the submission of your manuscript to the evaluation committee in November 2024. Only possible because of your character, your energy, your drive, and your determination. As a result, this laudatio is a little longer, I apologize, Pro-Rector, than usual, as there's so much to talk about if you attempt to describe the achievements of Dr. Vats. So we first met online in an MSACL session in November 2020. This was COVID still going on, and during the Q&A session at that meeting, you impressed me with the clarity of the questions you asked, not having a background in mass spectrometry. Then you approached me to see if you could join our team, even though you had already secured a PhD position in New Zealand. But the New Zealand entry requirements, because of COVID, were challenged by the global pandemic, and lucky for us, you decided not to go to New Zealand and apply for a position here as an early stage researcher in the Food Tranet program in 2021. This was a Marie Skłodowska-Curie action program that just got funded and led by Nives Ogrinch, who actually one of your opponents today. Nives, I also want to thank you for your coordinating role in the Food Tranet Consortium and all your support along the way for Mudita and the entire Food Tranet team. It has helped to start new research directions that now are gaining substantial traction on the Brightland campuses in Limburg, and that was in part your doing, Mudita. So Mudita, you came to us as a microbiologist with a little bit of MS experience, but an incredible eagerness to learn more. That curiosity to learn, combined with that unstoppable drive, transformed you very quickly into a true analytical researcher with a rapidly growing skill set, especially in mass spec. Before you knew it, you were sectioning, scanning mushrooms, established a collaboration with the Technical University of Munich, visited vineyards, sectioning plant-based alternative protein burgers, and so on, as we heard a lot about today. In the early days, towards your first paper, you frequented not only the farm and the food, but particularly the supermarket, because you went not collecting samples, but you went grocery shopping, particularly for the experiments, and the chanterelles were a little bit more difficult to get, and filled the lab with umami smells, the perks of food chemistry from farm to table. You kept challenging yourself in challenging projects filled with innovations. Throughout the process, you picked up knowledge from all the team members, but in particular your two co-promoters, Berta Pastor and Eva Kuipers. With all the changes happening along the way, it's a beautiful example how team science can work, and even if the topic is a little bit different than usual. So thank you both as well. Mudita, your participation in the FoodNet program also demonstrated a commitment to collaborative research and knowledge sharing, which ultimately drives innovation in the food industry, and we've heard a lot about that today. Through these efforts, you've played a role in promoting healthier food options and enhancing the overall well-being of society, something you should be really, really proud of. During your time here in Maastricht, you have always expressed how important it was for you to make a difference in the world. As a person, and through the impact of your research. There have been times, and one time in particular I can remember, when you perceived your own dissatisfaction in your results and expressed that you expected really more of your work. You raised the bar high for yourself. But I want to give you a reminder. Every contribution, small and big, makes a difference. The ultimate long-term impact is perhaps not clear at once, but is there for everybody to see, and has brought you where you are here today, a big accomplishment, and one to cherish for the rest of your life. So promise me, never sell yourself short again. I also want to make one comment on your thesis cover. The cover does not only have your name on it, but your brother also put a picture of you center stage. A characteristic dreamer, head in the clouds, thinking of all the agro-food related topics in your thesis. But maybe more importantly, the open attitude depicted in that image of you is exactly how we got to know you. Never lose that. It will get you very far in your career, and my compliments for your brother for capturing that in that beautiful way. The other thing you excelled at was collaborative team science, and I can come back to that again. With John Penders and Paul Saveklal and their microbiology teams, you could practice your microbiology skill. John, I'm happy that the work in this thesis led to our collaboration and looking forward to more to come. The next trip went to Italy to visit Michele Suman at Barilla, where on a food trend at Secondment, you worked on wheat and its processing into pasta and all kinds of other observations you could do with imaging mass spec. The pasta MSI results didn't make it into your thesis, but I'm sure we'll complete that story in the not too far future. Michele, thanks for your help in the process, and I hope that new projects will follow in the future. You also engaged in many other collaborations with Nana Bjarnol's group in Copenhagen, where you learned to section the wine leaves. And these leaves, of course, were gathered in collaboration with Chris Pelzer and Jannie Peters in Nijmegen. And Chris and Jannie are here in the audience. Thank you for your collaboration. And Chris, you've heard what the real story is. And Mudita, the organic oils, she has her doubts. We can discuss that over a glass of wine, I think. And subsequently, you studied all of these leaves here at M4I with MSI. Together with DSM and the food crew, with your paronyms and Theo, you started to image plant-based alternative burgers and their ingredients. Your research can now aid in the accurate classification of ingredients in plant-based foods, supporting transparency and informed choices for consumers. So, Dr. Vats, you've pushed all of these very different collaborative teams, and none of that would have happened without you. And remember, ladies and gentlemen, she did that in just 3 years. Now it's time for the next step in your career. And I'm happy to be able to say that you will be with us for a little while longer, using your collaborative skills and your drive in our collaborative open research education laboratory at M4I. I'm glad that we'll keep your positive energy around to drive many more projects forward in the years to come. You complement the team perfectly, and I'm sure we'll keep on driving scientific discoveries forward. So, Dr. Vats, Mudita, congratulations once again on the honor you've obtained today. It's been my privilege to supervise you, and I've enjoyed every minute of our interactions. I want to extend my congratulations to your family, your mother present here today, and your father and brother and others online. They are probably the only people at this moment in time that are prouder of you than I am. Congratulations.
Thank you, Ron.
Dear Dr. Vats, does it feel good? Feels good.
Yes.
I would like to congratulate you also on behalf of Maastricht University. You did a great job. It was a very nice presentation. There was an excellent response to the questions you were giving or receiving, and I would like to compliment you with this. In my compliment also, I would like to add your promotion team, who have guided you in this short time, just 3 years and 1 month. And I would like to compliment you also that you came all the way from India, and you did not choose New Zealand, but you went to come to the Netherlands. It's a big compliment. In my congratulations also, I put your family. I understand your mother is here. And I would like to also thank the members of the Corona who took the time to be here with us. Also, Dr. Gradinic from Ljubljana, that you came all the way to visit us over here. And by this, I would like to come to a conclusion, but I would say we have listened now for 45 minutes about burgers, and our sensory, at least my sensory processes are in that way that if you speak about food, you get a feeling about food, and I think it's time for a reception now. And I would also like to mention one thing, which I wrote here in my notes. You talk about burgers, but we have our Maastricht burger, of course, our Mosa meat, yes. And I would have been interested to see how you that incorporated here in your studies as well. Ladies and gentlemen, I would like to come to a conclusion, and for the conclusion I use my hammer, which I have right over here, and I conclude this session officially. How do we proceed? We're going to have a reception which will be in our rafter, and you don't have to wait for us because we're going to stay here and we're going to make a picture with Dr. Schumann over here at who is present online. We're going to make a picture on the stairs of our university, and then in approximately 7 to 8 minutes we will follow you in the rafter. You don't have to wait for this, and you already can start with processing all your tasty experiences in your smell, and I would like to please enjoy. Thank you very much.
Thank you.
They can hold it for you. Yes.